Good afternoon, everyone. So today we are going to discuss sixth lecture on uniform continuity. Okay. So let's start for today's lecture. Okay. Hope you are good and doing well. Okay. So in previous two lecture we have seen these following theorems. Okay. I am writing those results. Okay. First result is that if A belongs to R and F close interval A to infinity be a continuous function such that limit x tends to plus infinity fx exists, then f is uniformly continuous. Okay, continuous. Now see that if A belongs to R and you are taking closed interval A to infinity whose codomain is R, be a continuous function such that limit exists at infinity, then f is going to be uniformly continuous. But this is a sufficient condition, not necessary. We can have an example of a uniformly continuous function on a domain like this. What function is, but the limit at infinity does not exist. For example, you can see this. For example, you can see this because we have seen this theorem in previous lectures and we have seen some examples on this theorem. But I am saying that this condition is necessary. If function is continuous on this domain and limit at infinity exists, then function is uniformly continuous. Okay. But I can have a function which is uniformly continuous and limit at infinity does not exist. For example, you can see this example. So I am taking fx is equal to x on 0 to infinity. Okay. Is a uniformly continuous function. But limit x tends to infinity. Fx is what is this? This is infinity. It means limit does not exist. But still function is uniformly continuous. Does not exist. Limit does not exist. Okay. But function is still uniformly continuous. Okay. Similarly, second result we see this. Okay. This result. Second. If f R to R be a continuous function such that limit x tends to minus infinity fx and limit x tends to infinity fx exist, then f is uniformly continuous on R. Okay. So similarly, we will have a function which, so this theorem is that if function is continuous and limit at minus infinity and plus infinity exists, then function is uniformly continuous. So I will give you, so this condition is sufficient, not necessary. So I can have an example of a continuous function, uniformly continuous function on R, where neither limit exists, okay, but still function is uniformly continuous. For example, I am taking this example, again same example. What is that? Fx is equal to x on R. You see that this function is uniformly continuous. We have already seen uniformly continuous on R, but neither limit minus infinity. What is that? That is minus infinity, and nor limit x tends to plus infinity fx exists. Still function is uniformly continuous. Okay. Okay. So similarly, we can find other examples. Okay. For example, I have proved one result also, that if f is uniformly continuous, f is continuous on open interval a to infinity and limit infinity exists, then function is uniformly continuous. So we can also find example where function is uniformly continuous on open a infinity and limit at infinity does not exist. Same example, fx is equal to x you can take. Okay. Now I recall one thing. In our first lecture of uniform continuity, lecture 1, we have seen that the functions sin x, cos x, sin square x and cos square x are uniformly continuous on R. In first lecture we have seen how we prove this. We saw that these functions are Lipschitz functions, and we said that these functions are going to be uniformly continuous, because in first lecture we have proved that Lipschitz functions are uniformly continuous functions. So sin x, cos x, sin square x and cos square x, all are these functions Lipschitz functions, so they are going to be uniformly continuous. We have discussed such things in lecture 1. Now we want to prove more general result. For example, if you see that sin x, cos x, sin square x, cos square x, they are continuous functions on real line. You observe that these are functions which are continuous on real line, and you also observe that these functions are periodic functions. Okay. So we are going to prove a result that if a function is continuous on real line and it is a periodic function, it is going to be uniformly continuous. Then by this fact, sin x, cos x, sin square x and cos square x are going to be automatically uniformly continuous. We will prove this result now onward. So before that, let's define what is periodic function. So periodic function. Let f R to R be a function Okay. Then T, then F is said to be periodic function on R if there exists T greater than 0 such that f x plus T is nothing but fx for all x belongs to R. The smallest such T is called period of f. Okay. So a function such that there exists T greater than 0, fx plus T is equal to fx for all x belongs to x. Then such function is called periodic function. The smallest such T, there can be more than one T, okay, which satisfies this condition fx plus T is equal to fx for all x belongs to x. We are choosing the smallest one which satisfies this. It is called periodic function or period of that function. Okay. Okay. For example, I am telling you which are periodic function. For example, I am taking this. So you take sin x, fx is equal to sin x. So you take t is equal to 2 pi. So f x plus 2 pi, what is that? Sin x plus 2 pi. And we know that sin 2 pi plus x, what is that? It is sin x. So that is fx. So I have x plus 2 pi for all x belongs to R. So sin x is periodic function. Okay. Same thing if I take t is equal to 4 pi. T is equal to 4 pi. It means, okay, then we have x 4 pi. That is sin 4 pi plus x. Then still it is sin x. So I have told that more than one t can exist, but we will take a smaller one that is called period of function. So sin x is a periodic function and its period is smallest t which satisfies this. 2 pi is the smallest one which satisfies this. Okay. And its period is 2 pi. Okay. Similarly, you can check that cos x, sin square x and cos square x, sin x plus cos x, all are periodic functions with period with period 2 pi. Okay. With period 2 pi. Now observe one thing. If f R to R be a periodic function, then periodic function with period let's say t, then for any non-zero integer n belongs to z minus 0, I'm taking non-negative integer, then I have for any non-negative integer we have what we have f x plus n t is nothing but fx for all x belongs to R. Okay. If you have find a period, okay, then you take its non-negative multiple. That will be also serve the purpose of sum t. Okay. Okay. It means function repeats after n multiple of t, where n is non-negative integer. Okay. But when we talk about period is smallest p, smallest positive number. After that, function repeats itself. Okay. Now we are going to prove a result theorem. Let f R to R be a continuous function okay if f is periodic, then f is uniformly continuous on R. Okay. So every continuous and periodic function on R it is going to be uniformly continuous. If we can prove this result, automatically sin x, cos x, sin square x, cos square x, sin x plus cos x, sin x minus cos x, all these functions are going to be uniformly continuous. Okay. Because these functions are, we already know that these functions are continuous on R. Okay. So let's see its proof. So let f R to R be a continuous function with period t greater than 0. Okay. Now what does it mean? For example, you see f my sin x. For imagination, what you will see? This is real line. So how sine functions we have? Its graph is look like this. Okay. Okay. So, okay. So let's say it is my graph T. This is period. So what is period? Period is T. So this is my graph. After this T, x is equal to T. After stage T, it is repeating itself again. And next it is again repeating itself. If we go backward, still it is repeating backside. So this function is periodic function. Okay. Okay. So you fix. So I am fixing this domain. So I am taking this domain. So I am fixing. Let x naught belongs to R. So I am considering this domain. Consider the domain x naught plus t. That is subset of R. Because function is periodic, whatever graph the function have in this interval, it will have the remaining domain. Okay. Okay. So now you see that suppose I am considering, so my function is this. So let this is my x naught and this is my point x naught plus t. So in this domain, function is this. So in rest of the domain, function will be look like same thing. So I can write my domain R by this way. I can write n belongs to Z minus 0 x naught plus nt. Okay, if I am taking n positive, it means the interval is in increasing direction. If I am taking n is equal to negative, it is in decreasing direction. Okay. Okay, so R I can write like this. Okay. So now you see that in this domain my function is characterized. Okay. So I know that in this interval function is continuous, so it is uniformly continuous. Okay. But what about other? If I take any two point in this domain, x1 point, x2 point I am taking here. Okay. So it is fine because in closed interval function is uniformly continuous. So fx minus 1 minus fx x2, difference will be less than epsilon and corresponding delta will exist. Okay. But if you see that both these points exist here somewhere, x1, x2. Okay. But you can consider same point. You can consider same point here because function is periodic. You can select another point y1, y2 here whose difference is same as x1, x2 difference and their value is same. fx1 is equal to fy1, fx2 is equal to fy2 because function is periodic. Suppose some point is existing here, some point is existing here. So same thing you can do. You can select a point here and some point here. Okay. Still the case is settled down. So it is to prove this theorem, it is sufficient to consider this domain. To prove this theorem, observe that to prove this theorem, it is sufficient to consider the domain. Which domain I am considering? To consider this domain. So you are taking x naught plus t. You also add one more domain, x naught plus t, x naught plus 2t. You also add this domain, x naught minus t, x naught. So this domain is nothing but x naught minus t, x naught plus 2t. Okay. So if I can show that function is uniformly in this domain, so automatically function will be uniformly continuous on whole real line, because you selecting a point, function is periodic, we can select same point, same distance, whose functional value are same. The theorem is going to be reduced to show that function is uniformly continuous on this domain. Okay. So now I am taking this domain. Okay. To R. Now is a continuous function, because f is continuous on whole real line, so function is continuous on this. But this is closed interval. This is closed and bounded interval. We know that every continuous function on a closed and bounded interval is uniformly continuous, so it is uniformly continuous. So f is uniformly continuous on x naught minus t, x naught plus 2t. So this implies f is uniformly continuous on R. Hence the theorem is proved. Okay. So by this theorem, what we conclude? Conclusion. Since sin x, cos x, sin square x, cos square x, okay, sin x plus cos x, sin is x minus cos x, all are continuous function. All are uniformly continuous function because they are continuous, uniformly continuous function on R, because they are continuous and periodic functions on R. Okay. So what we have proved, that if a function is continuous and periodic on R, it is going to be uniformly continuous, because sin x, cos x, sin square x, cos square, sin x plus cos x, sin x minus cos x, and you can see other function also, sin square x plus cos square x, sin square x minus cos square. These are also continuous and periodic on R, so they are uniformly continuous. Okay. So in this lecture we have seen two things. We have given some counter example to the theorems. Such theorems are sufficient conditions to showing uniform continuity, but we have shown that still the conditions are not satisfying, functions are going to be uniformly continuous. And we have given example fx is equal to x. We have proved next theorem. We have discussed periodic function, and we have shown that if function is continuous on R and periodic as well, so function is going to be uniformly continuous. By this theorem, we have immediately saying that sin x, cos x, sin square x, cos square x, sin x plus cos x, sin x minus cos x, all are uniformly continuous function because they are continuous and periodic function on R with period 2 pi. Okay. So thank you very much for today's lecture. Now, so this topic is completed. Now onward we will discuss problem sets. Okay, 2 or 3 lectures on it. Okay, so thank you very much for today's lecture. You can comment on this for this lecture on my YouTube channel. Okay, please like, share, subscribe, and comment. Okay, thank you very much for today. Thank you very much.